Today's program, briefly, today we are in the morning colloquial talks. Can you hear? Oh, sorry. Today in the morning we have the colloquial talks, and in the evening public talks. In between at 3 o'clock we have a foundation stone laying function between 3 and 4. So let me just read out the program today and then hand over the proceedings to the chairs. Today's first talk is Ashok Sen. Second is Ramanan, concept of moduli. Third one is Benedict Gross. After that is a lunch break. Then there is a foundation stone laying function, and then again in the evening 4:15 to 5:15 is TV Ramakrishna's talk, and 6 to 7 is Umesh Vazirani's talk, public talk. So with this, I welcome you today again. Good morning, and let us start with today's function.
Okay. Good morning. So we'll start the morning session with a talk by Professor Ashok Sen from Harishchandra Research Institute. Now, Ashok is well known to the academic circles, so he doesn't really need an introduction, but I'm going to spend a couple of minutes saying a few things about him. In fact, he's not only well known in academic circles, but he's also practically a household name in India, because today morning I received a phone call from my mother saying, "Is Ashok Sen talking today?" So Ashok did his BSc from Presidency College, Calcutta, and his master's from IIT Kanpur. Then he went on to his PhD in Stony Brook with Professor Sturman, who's here in fact. He started off with a bang in string theory in the early days of string theory with some many important works. The earliest thing I can remember is his work on conformal invariance, the role of conformal invariance in string propagation. He followed that up with many important works, such as establishing S-duality, the strong-weak duality in superstring theory, black hole entropy, counting microstates, and then he did his pioneering work in unstable D-branes and tachyon condensation. His work in string theory is well known to all the string theorists, and I don't need to tell you about that, but I should also mention that he's received, in honor of these works, he's received many awards, and I'm just going to list a few of the important ones. The ICTP Prize, the Bhatnagar Award, then he was elected the Fellow of Royal Society in '98, the Padma Shri 2001, then more recently the Infosys Prize 2009, and very recently the Foundational Physics Prize last year. So I don't want to take much more of your time, but he's been doing some very interesting work recently on black hole entropy and quantum gravity, and I'm going to have the pleasure to welcome. And I'd request everyone to switch off your mobiles.
MSc giving this talk, and it's always nice to come back to this institute. So what I plan to do today is to give a general overview of holography and quantum gravity, and then I'll try to describe some of the work we have been doing in this subject. So here is the plan of the talk. I'll start by describing what is holography, okay, what we mean by holography in the context of quantum gravity, how do we find examples of holography, and how do we test holography. So let me begin with the question, what is holography? Okay, and this can be stated in one sentence, although many of the words in this sentence needs explanation, which I'll try to provide in the next few slides. Okay. But the statement of holography is simply that a theory of quantum gravity on certain space-time, which are commonly known as the anti-de Sitter or AdS space-time, is equivalent to a conformal invariant quantum field theory, or in short CFT, in one less dimensions. Okay. And the important point here is one less dimension, and this is the reason why this subject has been given the name holography, because as you know, in hologram we encode three-dimensional information on a two-dimensional surface. So as I said, this statement has many words which may not be familiar to you. So let me begin by defining those words in the first place. So first of all, what is an AdS spacetime? Okay. So for this we can begin with a flat spacetime, which most of us are familiar with, but we will take a slightly different kind of flat spacetime. We will take a flat spacetime which has n space coordinates, which are denoted by w1 to wn, and 2 time coordinates, which are denoted by y1 and y2. So this is an n-dimensional, n plus 2 dimensional spacetime, and in this space we describe an n plus 1 dimensional subspace by this simple equation. Okay. And as you can see, if we had changed some of the signs, okay, if these had been plus and this had been plus, this is exactly how we describe an n plus 1 dimensional sphere by embedding it in an n plus 2 dimensional Euclidean space. Okay. So this space that we define this way, this is of course an n plus 1 dimensional space because we have one equation on n plus 2 coordinates. Okay. This space locally is what is known as the n plus 1 dimensional AdS space, or in short AdS n plus 1. Now often it's useful to introduce some intrinsic coordinates on the space, okay, instead of thinking of this as being embedded in one higher dimensional space. Okay. And similarly we can introduce intrinsic coordinates on AdS space. Okay. So what you can show after some coordinate transformation, that the AdS space can be described by these n plus 1 coordinates, x0, x1 up to xn minus 1, this is n coordinates and another additional coordinate z, such that the metric which measures the distance between 2 points, or the square of the distance between 2 points in AdS, is given by this formula over here. Now if you are not familiar with this form, the metric written in this form, okay, so what this tells us, that this is the proper distance element, ds is the proper distance element, so ds square is the square of the proper distance, and this tells us that if we have 2 points in this space time separated by dx0, dx1, coordinate separation dx0, dx1 up to dz, then this is what gives the proper distance between the 2 points. Okay. R here is a constant, it's the same constant that appeared in the previous slide over here. Okay. When we introduce intrinsic coordinate, R appears explicitly in the metric. Okay. And if you are familiar with the form of the metric in the matrix form, okay, this is what it means. The same metric, when you write out in a matrix form, it's just a diagonal matrix with minus 1, which comes from here, and all other diagonals being 1. Now one point you can notice here is that if we take z goes to 0, if z becomes smaller and smaller, okay, the metric components go to infinity. And physically this means that the distance between points separated by finite difference between the x mu's, okay, if dx remains finite, then the distance goes to infinity. Okay. So the distance between the x mu's become larger and larger in this limit as you go, as z goes closer and closer to 0. So here I have written the same metric again. Okay. And we see from here clearly that z equal to 0 is somewhat special because that's where the distances diverge. Okay. And this is called the boundary of the anti-de Sitter spacetime. Okay. So you can think of that, so this is a pictorial representation of the anti-de Sitter spacetime. Now of course I cannot draw an n plus 1 dimensional space, so what I have done is that I have taken z as a spatial coordinate, so z direction is the vertical direction, and the horizontal direction stands for all the coordinates x0, x1 up to xn minus 1. Okay. So z equal to 0 is called the boundary of anti-de Sitter spacetime. Okay. But for all practical calculations, we place the boundary at a finite value of z, okay, finite but small value of z, okay, and then at the end you can take the limit epsilon to 0. Okay. So when in future, when I refer to the boundary of anti-de Sitter space, this is how it should be understood. So again, you see the metric. Okay. Now, often in physics, okay, it's useful to analytically continue the time coordinate to imaginary values. Okay. In fact, we do this also when we study special relativity often. Okay. So, analytically continue the time coordinate x naught to imaginary value. So, x naught goes to I x naught, and if you do that, then the metric on AdS goes over to what is called the Euclidean AdS space. Okay, and that's given by this, right? All I have done here is that I have replaced x naught by I x naught, so the minus sign has become plus sign. Okay. And now we see that if we consider the boundary of z equal to epsilon, so z is constant, so dz vanishes. Okay. And so the metric on the boundary, which is of course an n-dimensional Euclidean space, okay, because z is constant, that has a flat metric, right, because the only relevant part of the metric now is this. Okay. So if we take 2 points on the boundary separated by dx0, dx1 up to dxn minus 1, this is what gives you the square of the proper distance between those 2 points. So this finishes our introduction to AdS spacetime, okay, or anti-de Sitter spacetime. Okay. Now I have to introduce what is a CFT, okay, which is a short form for conformal field theory. Okay. Now CFT is a special class of quantum field theory. So first I have to define quantum field theory. So quantum field theory is a quantum theory where the basic dynamical variables are fields, okay, like for example the electromagnetic fields. Okay, so one particular quantum field theory can be obtained by starting with the classical theory of electromagnetic fields and then making this into a quantum theory. Now CFT is a special class of quantum field theories. Okay. The subscript n in CFT in our notation will stand for an n-dimensional, this quantum field theory defined on an n-dimensional flat space-time. Okay. And the special property that this quantum field theory has is that besides being Lorentz invariant, okay, besides being invariant under Lorentz transformations, okay, it's also invariant under what is called the scale transformation and spatial conformal transformation. Now what is scale transformation? Scale transformation has a simple form. It just simply says that all the coordinates are scaled by some parameter lambda, some arbitrary parameter. So the theory remains unchanged under such scaling. Okay. Conformal transformation is a little more complicated. Okay. So it's parameterized by 3 defined parameters or n defined parameters in n dimension, okay, b mu, and this is the way the conformal transformation acts. Okay. So lambda and b mu here are arbitrary parameters. Okay. So in theory, a quantum field theory that's invariant under Lorentz transformation and also invariant under these set of transformations is what is known as a conformal field theory. Okay. So as an example, we can point to the theory of electromagnetic fields without sources. This is a theory that is known to be conformal invariant in 4 space-time dimensions. Okay, so the Maxwell's theory of electromagnetism, when you make it into a quantum theory, it actually gives rise to not just just one quantum field theory, but also a conformal invariant quantum field theory or a CFT. And as I have already said, we will denote by CFTn a conformal field theory in n space-time dimensions. So I have now introduced, okay, both sides of the holography, okay, AdS space-time and conformal field theories. Okay. And now we can give a statement of holography. Okay. So it says that a theory of quantum gravity in an n plus 1 dimensional AdS space is equivalent to a conformal field theory in the n dimensional space-time that sits at the boundary of this n plus 1 dimensional AdS space. Okay, we have seen that we have introduced the notion of boundary of AdS. Okay, so this is a statement of holography. A theory of quantum gravity in the n plus 1 dimensional AdS space is entirely equivalent to a conformal field theory on the boundary of AdS space. Okay, and this is the reason why this subject is called holography, because essentially it's a statement of equivalence between an n plus 1 dimensional theory and an n dimensional theory. Now, a more precise statement of this was provided. So this was first proposed by Mallasena, but a more precise statement was given by these authors over here, okay, who told us precisely what it means, right? What quantities in AdS n plus 1 maps to what quantities in an n-dimensional conformal field theory. Okay, and so this is a little more technical. Okay, and what the technical statement of this equivalence is simply that the correlation functions of operators in the conformal field theory, okay, so these are what are the physical quantities in the conformal field theory. These are given by the partition function of quantum gravity, with appropriate boundary condition on the various fields at the boundary of Euclidean AdS. Okay. So if you don't follow this statement, it's not relevant. Okay. All I want to emphasize here is that there is a precise prescription, okay, which tells us that given any quantity in conformal field theory, what we should compute in AdS and vice versa. Okay. And what operators you choose in the conformal field theory are correlated with what boundary condition you choose on the various fields in AdS spacetime. Now, given the statement of holography, you could ask why is holography important? Okay. And the importance of holography goes in both directions. Okay. Often one finds that it maps difficult problems in quantum field theory or conformal field theory to simple questions in classical gravity in appropriate limit. Okay. So in the most general form, the holography is a statement of equivalence of a conformal invariant quantum field theory and a theory of quantum gravity. But by taking appropriate limits, okay, we can simplify one side or the other. Okay. For example, by taking an appropriate limit, we can make sure that the quantum gravity can be approximated by classical gravity, okay, and then that can be used to solve difficult problems in quantum field theory. But more importantly, the correspondence goes the other way. Okay. Holography allows us to give a precise definition of quantum gravity in AdS spacetimes by relating it to an ordinary quantum field theory whose rules are quite well understood. Okay. So here I should just say that the quantum field theories are well-defined objects. Okay. While it may be difficult in practice, okay, to do computations, in principle we can imagine putting a quantum field theory on a computer, and if you had a sufficiently powerful computer, we could compute everything that we want to compute in that theory. Okay. Quantum gravity in AdS, on the other hand, is a less understood subject. Okay. At present, string theory is the only systematic approach to studying quantum theory of gravity in any background. Okay. And nevertheless, it's a difficult analysis, and so the holography in some sense gives a definition of quantum gravity in AdS spacetime by using the dual description, okay, or the equivalent description as a conformal field theory on its boundary. Now, this statement looks a bit surprising, right? How can a theory in n+1 dimension be equivalent to a theory in n dimension? Okay. One of them has gravity, the other one doesn't have gravity, right? What is this? What is the origin of this equivalence? Okay. And this is related to the question as to how do you find examples of holography? Okay. How, for example, did Mallas and I arrive at holography in the first place? Okay. Put another way, we can ask, is there a systematic way of deciding which theory of quantum gravity on AdS n+1 is dual to which conformal field theory? Okay. Now, at present, we know the answer to this only in a small class of examples. Okay. But when I say small class, I should also point out that each class actually contains an infinite number of examples. Okay. So the number of examples where we know how both sides of this conjecture very well, okay, is still infinite. Okay. And as I said, because at present string theory seems to be the only systematic way of defining quantum gravity in general backgrounds, okay, in particular anti-de Sitter spaces, we will restrict our discussion from now on to string theory. So let me just say a few words about string theory. So string theory is a quantum theory of gravity, okay, and the main idea in string theory is that elementary particles are replaced by one-dimensional string-like objects in this theory. Okay. Nevertheless, the string-like objects are taken to be very, very small, so that for all practical purpose they will behave like particles. Okay. But intrinsically the theory is quite different from the theory of elementary particles. So the elementary objects in string theory are strings, one-dimensional objects. But besides these fundamental strings, string theory also contains many other composite objects. Okay, these composite objects you can think of, okay, at a very crude level as being objects that are made of strings, okay, that are built by strings, okay, but nevertheless they are composite. Okay, just like a molecule is composed of atoms, okay, or an atom is composed of nuclei and electrons and so on. Okay. So the fundamental objects in a string theory are strings, but there can be other composite objects. Okay. And these composite objects could have either higher or lower number of dimensions. Okay. You can have composite objects of 0 dimension, particle-like composite objects, or composite objects of 2 dimension, for example, a membrane-like composite objects, and so on. Okay. As one particular example, we can mention type 2 string theory. This is one of the 5 consistent string theories, okay, which is defined in 10 space-time dimensions. This has an object that extends in 2 directions. Okay. So an object which extends in 2 directions is what we call membrane, okay, or a wall. Okay. So this is what I have said here. It's a membrane, also sometimes known as a D2 plane. Okay. This 2 here stands for the fact that it extends in 2 directions. Okay. D is technical word for Dirichlet, but it's not important for what we are going to discuss. Now in general, the dynamics of these composite objects is very complicated, and it involves infinite number of internal vibrational modes. Right. Just like, as we know, if you have a molecule made of atoms, right, then there are infinite number of various modes of the molecule, okay, the various vibrational modes of the molecule. Okay. Similarly, the dynamics of composite objects is always very complicated, involving infinite number of possible modes. Okay. But our interest will be to understand the dynamics of these objects involving low frequency or low energy modes. Okay. Now notice that I have said low energy and low frequency on the same as an alternate description, and that follows from quantum mechanics. In quantum mechanics, frequency and energies are proportional to each other, so low energy also means low frequency. Okay. So if you want to understand the dynamics of these modes, okay, in the low frequency limit, okay, then it turns out that the dynamics is described by that of a p-brane. Okay, dynamics of the p-brane is described by p-dimensional quantum field theory, or p plus 1 dimensional quantum field theory. Okay. So for example, the dynamics of a point particle for which p is equal to 0, okay, will be described by a 0 plus 1 dimensional quantum field theory, or in other words, a quantum mechanics. Okay. Dynamics of a string, which is a 1 brane, because string extends in one direction, will be described by 1 plus 1 dimensional quantum field theory. This plus 1 stands for time, okay, because time is always present. This is the number of spatial dimension that the object has, okay, and so on. Okay, so in general, if you have a p-brane, okay, which means a p-dimensional extended object, then the corresponding dynamics is described by quantum field theory in p plus 1 dimensions. So here I will consider a specific example of such a brane, okay, such a composite object, okay, and this example arises in a specific limit of string theory, okay, because it turns out that the string theory, although it was defined, it was originally formulated in 10 dimensions, or 9 plus 1 dimension, 9 space and 1 time dimension. In certain limit, which is also known as the M theory, string theory can actually be approximated by an 11 dimensional theory, okay, which is technically known as the 11 dimensional supergravity. Okay. And in this theory, there is a composite object that extends in 2 space directions. Okay. So as I already said, the composite object that extends in 2 space direction is like a membrane, okay, also called the M2 brane. This M stands for the fact that we have this object area arises in M theory. Okay. And just like once you have one molecule, you can put another molecule on top of it. Okay. In fact, you can put n molecules on top of it and study the dynamics of these molecules. Okay. Similarly, if you have one M2 brane, you can also have several M2 branes on top of each other. Okay, you can put several M2 branes on top of each other, okay, and ask what is the dynamics, okay, what is the theory that describes the low frequency or low energy dynamics of this system. Okay. Now I have already told you that low frequency dynamics should be described by some 2 plus 1 dimensional quantum field theory, okay, and in this case one can explicitly work out what this 2 plus 1 dimensional quantum field theory is. It's a complicated quantum field theory, and it's known as the ABGM model, okay, after the discoverers, okay, of this particular theory. Okay. And for those who are experts, okay, in 2 plus 1 dimensional quantum field theories, I should just point out that an ABGM model is a special case of 2 plus 1 dimensional Chern-Simons theories coupled to various matter fields. Okay, but for our purpose, it's just enough to know that there is some 2 plus 1 dimensional quantum field theory that underlies the dynamics of these M2 branes, okay, or the low frequency or low energy dynamics of these M2 branes. Okay. And this is not very visible. This theory is known to be a conformal field theory. Okay. So it's not only just a quantum field theory, it's also invariant under conformal transformations. Okay. So this is the CFT. Okay. So what I described above is one way of describing the set of n M2 branes on top of each other. Okay. But it turns out that there is another way of describing the same system. Okay. Because after all, string theory is a theory of gravity. Okay. So these M2 branes, okay, anything that carries mass or energy, okay, will produce gravitational field. So M2 branes also produce gravitational field, okay, and also other fields which are present in the theory. Okay. And as a result, we can describe this set of n M2 branes as solutions to classical equations of motion of gravity. Okay. And again, it's gravity, not just pure gravity, but also other fields which are present in the particular theory that we are considering. Okay. It turns out that the classical solution that describes a stack of n M2 branes, okay, corresponds to the zero temperature or extremal limit of a black membrane solution. Okay. So black membrane, I have to explain now what we mean by a black membrane solution. Okay. Now, but you probably have heard about black holes. Okay, black holes are objects in the sky, okay, which have the property that they are surrounded by some kind of event horizon. Okay, it's a hypothetical surface which acts as a one-way membrane. You can go from outside of the event horizon to the inside, but you cannot come out. Okay. A black membrane is a generalization of this black hole, okay, where the horizon, instead of being spherical, okay, and hence localized in space, okay, it's a two-dimensional subspace, two-dimensional space that extends that extends by infinite amount in both directions. Okay. So that black membrane, you can think of this as a wall, okay, in space-time, okay, and it has a property just like the horizon, that it acts as a one-way membrane. Okay. You can travel from one side of the horizon, from the outside of the horizon to the inside, but you cannot come out. Now, and that the reason that it happens is because the gravity is very strong at the horizon. Now, you might have also heard about gravitational redshift. Okay, this stands for the fact that if you put a clock in a strong gravitational field, it slows down. Okay, and the horizon of the black hole, in fact, has a property that the gravitational field there is so strong, okay, that any clock put on the horizon will slow down by an infinite amount, okay, as seen from the observer who is far away. Okay. So due to the gravitational redshift, the modes of excitation near the horizon of this black membrane appear to be of extremely low frequency. Right? A clock that slows down, in fact, not any clock, even the atom, okay, which has its internal clock, will also slow down. Okay. And as a result, if you put any system near the horizon, okay, the system will have extremely low frequency, okay, from the point of view of an observer who is sitting far away from the planes, okay, who is far away from the horizon. Okay. And so dynamics of these low frequency modes, okay, from this viewpoint will be given by M theory in the near horizon geometry, okay, in the geometry of the black plane or the black membrane near the horizon, right, because these low frequency modes come only when you take a system near the horizon. Okay. So you can forget about the rest, okay, if you are focusing on the low frequency modes, and you can consider M theory in the near horizon geometry of the black membrane. Okay. And this near horizon geometry for M2 branes turn out to be a space that is described by AdS4, a 4-dimensional AdS space, times a 7-dimensional sphere. Okay, I said that M theory is an 11-dimensional theory, and you see the total dimension of space-time adds up to 11 indeed, okay, but it has a specific form. It's a product of a 4-dimensional AdS space and a 7-dimensional sphere. So we say that we have two different descriptions of the low frequency dynamics of a system of n M2 branes. Okay. First of all, we can describe this as a conformal field theory, 2 plus 1 or 3-dimensional conformal field theory given by the ABGM theory. Okay. Or we can also describe this as an M theory in this background. Okay. These are alternate descriptions of the low frequency mode, the dynamics of low frequency modes of a system of n M2 branes. Okay. And this is what led Malleson to conjecture that these two theories must be equivalent. Okay. He provided some consistency checks. For example, the symmetries of the two theories match. The first theory, this one, has supersymmetry plus conformal symmetry, and this agrees with the supersymmetry and the geometrical symmetries of the second theory. Let me now turn to a second class of examples. Okay, as I said, there are a few examples where we know both sides of the story. Okay. So the second class of examples will in fact involve black holes instead of black membranes. Okay. Now these arise from the fact that in many string theories we have supersymmetric, okay, which are also called extremal zero temperature black holes. Okay. And a typical situation where this arises, okay, where you get black holes in string theory, is the following. Okay. We can begin with string theory, which is of course defined in higher dimensional space-time, but we can take that space-time to be the product of some compact space K times the 3 plus 1 dimensional Minkowski space. Okay. And this then effectively gives rise to some theory in 3 plus 1 space-time dimensions. If the compact space is sufficiently small, then you only see this 3 plus 1 dimensional space-time. Okay. And this includes gravity. Okay. Whatever theory you get in 3 plus 1 dimensional space-time of course includes gravity, because string theory is a theory of quantum gravity. Okay. And once you have a theory of gravity, okay, we can find black hole solutions in this theory. Okay. And in particular we can also take the zero temperature limit of these black hole solutions, which are called the extremal black holes. Okay. So there are some special limits of these black hole solutions. Okay. So again, by following the same logic, okay, if you want to study the low frequency modes, the dynamics of the low frequency modes in the background of these black holes, okay, we can argue that we can effectively focus on the near horizon geometry. Okay. And in this case, in the case of black holes, the near horizon geometry turns out to be a product of a two-dimensional AdS space, a two-dimensional sphere, and this compact space K that we had started with. Okay, so S2 here stands for a two-dimensional sphere labeled by the usual polar and azimuthal triangles. Okay. So this means that we expect that the low frequency or low energy dynamics of these black holes should be described by string theory on this space. Okay, string theory or a theory of quantum gravity on this space. Okay. So we say that if we can find an alternative low energy description, then again we will have an example of AdS CFT correspondence. Okay, one side of the story we have already found, okay, that is a specific string theory on this background. Okay. So if you can find an alternative description, then you have the other side of the story, okay, providing us an example of holography. So for this, to find the other side of the story, you have to look for microscopic systems which produces this black hole geometry in string theory on K times R3, 1. Okay. Just like for the case of two branes, M2 branes, okay, the M2 branes are the one which produces this near horizon, produce the near horizon AdS 4 times S7 geometry. Okay. Here you have to look for the analogs of the M2 branes. Okay. And this is not hard to identify. Okay. Typically one finds that the system that produces these near horizon geometries, this black hole geometry, are given by a combination of many different kinds of branes oriented in different ways along the compact space K. Okay. So instead of just having a stack of one kind of branes, okay, the black holes, okay, are more complicated objects, and they are produced by a combination of many different kinds of branes. Right? Some branes in this direction, some branes in this direction, and so on. Okay. Together they produce the geometry of the black hole. Now since many different kinds of branes are involved, the dynamics is usually more complicated. Okay. Unlike M2 branes, which are just one stack of branes, okay, here you have different kinds of branes, so you have a more complicated dynamics, but overall it will produce some kind of quantum mechanical system. And by examining the spectrum, what one finds is that it contains some degenerate ground states, and then there are of course excited states, but the excited states are separated from the ground state by some energy gap. Okay, this is the same, similar to what happens in the case of hydrogen atom. Okay, if you are familiar with that example, hydrogen atom has a ground state. Okay, that's of course not degenerate. Okay, and then there are excited states, but excited states are separated from the ground state by a finite gap. So you see that if we now want to take the low energy limit, okay, which is what we are supposed to do, because on the other side, okay, on this side we have arrived at this geometry by focusing on the low frequency or the low energy limits. Okay. So if you are interested in looking at the low energy limit, okay, then you only have to keep the ground state. Okay. So low energy description in fact is in this case is very simple. The low energy description is just a quantum mechanical system with a finite dimensional Hilbert space. Right? This finite dimensional Hilbert space basically contains the degenerate ground states and nothing else. Okay. So all of them have the same energy, as I said, and we can take this energy to be 0 by a shift. Okay, because the overall value of the energy is not very relevant in these problems. Okay. So this leads to another example of AdS safety correspondence. It's an equivalence between string theory or quantum gravity on this complicated space AdS 2 times S2 times K, okay, with a quantum mechanical system with finite dimensional Hilbert space at 0 Hamiltonian. Right? It's 0 Hamiltonian because all states have 0 energy. Okay. And I have discussed this in the context of a 4-dimensional space-time. That's why you get AdS 2 times S2 adds up to 4. But this analysis can be generalized to cases where the black hole is embedded in n plus 1 dimensional space-time instead of 3 plus 1 dimensional space-time. Okay. So these are two classes of examples that I described. Okay, there are many other classes of examples like this. Okay, in fact, the most famous one is what I have not described. That's the example of a duality between a 3 plus 1 dimensional quantum field theory and the dual geometry. Okay. But besides this systematic approach, okay, there is also another approach to finding examples of AdS safety correspondence. Okay. And that is simply to make a clever guess. Okay, you don't start from these brains and try to study the near horizon geometry and so on. You simply try to make a clever guess. You take some conformal field theory and try to guess what its dual AdS geometry is. Or you start from some theory in AdS spacetime and try to guess what its dual conformal field theory is. Okay. And this indeed has been successful. There have been many recent discoveries of such correspondences involving higher spin theories of gravity. Okay, and here are some of the authors who found such examples. So now I turn to the last part of the talk, okay, the third part. How is an AdS safety correspondence tested? Okay, I told you how to motivate a given AdS safety correspondence. Okay, a particular theory of quantum gravity in AdS is equivalent to some particular quantum field theory which is conformally invariant. Okay. But is it possible to test it explicitly? Now it's clear that in order to test AdS safety correspondence, we need to compute some quantities independently on both sides. Okay, and then we can compare their value and see if we get the same result. Okay, that's how the AdS safety correspondence can be tested. Now on the CFT side, these quantities depend on various parameters of the CFT. Okay, and in the example of N2 brane that I described, it depends, for example, on the number of N2 branes, right? You can take different numbers of N2 branes labeled by N, and this gives rise to different conformal field theories on that side. Similarly, on the AdS side, the quantities depend on various parameters of AdS, just like the size R of AdS. Okay, if you remember, I had introduced this parameter R at the very beginning, okay, which appears as an overall factor R square in front of the metric. Okay. So the calculation on the AdS side will depend on this size R. Okay. And the AdS safety correspondence, okay, tells us precise relation between these parameters. Okay. So there are, for example, in this example, R and N are related by some specific equation, okay, which I have not written down, but it's an explicit relationship that tells us what value of N will correspond to what size R of AdS and so on. So in principle, we should be able to compare the various quantities in AdS and CFT as functions of these parameters. Okay, we calculate quantities in AdS as a function of R, we calculate quantities in CFT as a function of N, and then we compare. Okay, after translating R to N by the relationship that follows from AdS CFT correspondence. However, this is not very easy, because what happens is that typically quantities which are easy to calculate on one side in certain limit of the parameters are difficult on the other side in the same limit, and vice versa. Okay. And this is the reason why testing AdS CFT is difficult. Okay. This is a duality, which is an equivalence between two systems. Okay. But the quantity, okay, which can be calculated easily on one side turns out to be difficult to calculate on the other side and vice versa. Okay. That's why it's difficult to test it, but that's why also it's useful correspondence. Right? Because once you are convinced of a given AdS CFT correspondence, you can calculate difficult quantities on one side by using simple methods on the other side and vice versa. Okay. Despite this difficulty, okay, many clever tests of AdS CFT have been performed by focusing on special quantities and limits. Okay. And I will not be able to go through the full details of all these tests, okay, but I should just add that it's not just that people have made this conjecture without in vacuum. Okay, there are many clever tests that have been performed by now. Now most of these tests involve a limit in which the gravity side of the calculation becomes classical. Okay, as I said, you have both sides, okay, the conformal field theory and the gravity side, both are labeled by certain parameter. Okay. But typically the limits in which the tests have been performed, okay, the gravity side, okay, becomes classical. Okay. And there is good reason for this. Okay. The good reason is simply that dealing with quantum gravity is a very difficult problem. Okay. String theory in principle tells us how to calculate in quantum gravity, okay, but in practice, okay, using string theory to do computation in quantum gravity is not an easy task. Okay. And that's the reason why the tests have mostly focused on classical gravity. Okay, this of course requires taking appropriate limit of parameters where the quantum effects of gravity can be ignored. Okay, for example, if the size of AdS can be taken to be large, okay, then we can be sure that quantum gravity effects are not important. Classical gravity is good enough. This, however, is not good enough if you are to use holography as a definition of quantum gravity. Okay, as I said, one of the uses of holography is that we can use quantum field theory to define quantum gravity. Okay, but for this it's important to explore whether the holographically defined quantum gravity, okay, namely the definition of quantum gravity through the dual conformal field theory, whether it follows the usual rules of quantizing gravity as a perturbation expansion. Right? Given a quantum theory of gravity or any quantum field theory, we have some usual notion of how to quantize it and how to carry out perturbation expansion, and we should be convinced that holography might have given a new way of defining quantum gravity, but it should agree with our old ways of defining quantum gravity wherever the old ways can be utilized. And so this makes it important to test if the AdS CFT correspondence holds beyond the classical level with the usual rules for quantizing gravity or string theory. Okay, if it turns out that the holography gives a definition of quantum gravity, but it's quite different from the usual method for quantizing gravity, okay, or if the results of holography is quite different from the usual results for quantizing gravity, then you will be a little doubtful about whether it's really defining quantum gravity in the way we want quantum gravity to behave. So as an example, let me consider AdS 2CF21 correspondence. This involves black holes. Okay. So for this, let's recall that AdS2 arises as the near horizon geometry of extremal black holes, and CFT1 is a quantum mechanical system with a finite dimensional Hilbert space. Okay. And one can follow the usual rules of AdS CFT correspondence to see what it implies in this case. Okay, what quantity should be equal to what quantity. Okay. And the simplest such relation is given here. It tells us that omega, which is the total number of states in the Hilbert space, okay, or the dimension of the Hilbert space, okay, is equal to the partition function of quantum gravity in AdS space. Okay, so ZAdS is the partition function computed by carrying out path integral over all fields in this background. Okay. So this is a simple enough relation. We can ask, can we test it? And in this case we have some hope of testing it, because in some examples this number can be calculated exactly, okay, as a number. Okay, this is just the dimension of the Hilbert space, and by solving the quantum mechanics problem you can actually calculate this number exactly. But the exact computation on the other side, okay, the partition function of quantum gravity in AdS space is difficult because it requires exact computation of quantum gravity or string theory, okay, which you don't know how to do at present. You only know how to use perturbation theory. So the strategy here will be to take this exact result for omega, okay, but don't consider the exact, don't try to analyze, try to reproduce that exact result. We take the exact result and study it in a limit if the leading contribution to ZADS would come from classical string theory or classical gravity. Okay. Then the first subleading contribution will come at one loop. Okay, one loop. Okay, it's a technical word for the first order correction to classical result and so on. Okay. So then we can organize the calculation on the ADS side as a perturbation expansion. Okay, the leading term being the classical result, then the first subleading term being the one loop result and so on. And we can compare this with the CFT results. Okay, so even though the CFT results are exactly known, okay, we don't use the exact results, we try to expand it in a series and compare the coefficients of expansion in that series. Now in the examples where omega is known, I said that there are some examples where this number is known exactly. Okay, one finds that the size of the ADS2 is determined by the charge of the black hole. Okay, I already said earlier that there is a correspondence between the parameters on the ADS2 side and the parameters on the black hole side. Okay, so here is one relation, the charge, the size of ADS2 is determined by the charge of the black hole. Okay, and in particular large R corresponds to large Q. Okay, so if you want to make the ADS large enough, okay, large size, so the quantum gravity effects are small or can be ignored, okay, then you have to take the black hole to carry large charge. Okay. And in this case, the leading contribution to omega or log omega for large Q will correspond to the classical result for log ZADS, because as you take Q to be larger and larger, R becomes larger and larger and quantum effects become less and less important. Okay. So this is the first thing you would like to do. Right? Take the leading contribution to log omega for large Q and compare the classical result for log ZADS. Okay. And this works in all examples where it has been tested. Okay. In fact, this is the famous result due to Strominger and Waffer, who first tested the equivalence between the Bekenstein-Hawking entropy of the black hole and the result of microscopic counting. Okay. So the microscopic counting stands for omega and the Bekenstein-Hawking entropy is the classical result for log ZADS. Now, when one examines the exact result for omega, okay, as an expansion, one finds that the first subleading correction to log omega is of order log Q. Okay, so the leading term goes as quadratic in Q. Okay, it grows quadratically with Q, and the first subleading correction goes as log Q. Okay, and then there are powers which the negative powers of charge. Okay. So this subleading correction in log ZADS should come from one loop contribution to the partition function involving massless fields. Okay. Because one loop is the next order correction. Okay. And we can ask, do they agree with the log corrections to log omega that we calculate from the exact result? Okay, so this will be the test of ADS CFT beyond the classical level, right? Because we are studying one loop correction to the ADS partition function and comparing it with an appropriate correction to log omega. Okay. And so here I have shown some results. Okay, the details are not important. Okay, this column, for example, gives you various theories on various kinds of black holes where this has been done. This tells us how the various charges are scaled. Okay, so for example, lambda here is a large parameter in all of these, and Qi goes to lambda simply means that all the charges are scaled up equally, okay, to be large. Okay. This column gives the correction to log ZADS. Okay, this is the quantum gravity calculation. Okay. And the last column is the result from the log omega. Okay, you take the exact result for omega and then expand it out for large charge. Okay. And if you examine this table carefully, you will see that in all cases where this side is known, the question marks here simply stand for the fact that log omega has not been calculated in these models. Okay. But wherever both sides can be calculated, we see that there is perfect agreement between the two sides. Okay. So the coefficient of log correction indeed agrees, okay, between the two sides, and this establishes that ADS safety correspondence works not just at the classical level but also beyond, okay, at least at one loop quantum, at the level of one loop quantum corrections. Okay. Since I have run out of time, let me just say a similar analysis can also be carried out for ADS4 CFT3 correspondence. This involves the M2 bin. Okay, I have told that there is a correspondence between the M theory on ADS4 times S7, okay, and the ADGM model. Okay. And there the relationship, okay, one particular relation takes this form. The partition function on AdS is equal to the partition function of the conformal field theory. Okay. And again here it turns out that this side, okay, the conformal field theory side, the partition function can be calculated exactly as a function of n. Okay, n is the number of M2 branes. Okay, and you take that exact result, okay, and you can expand it out for large n. Okay, the large charge which you take the large n because the radius of AdS becomes larger and larger as you take n to be larger and larger. Okay. So in the large n limit, the exact result has an expansion of this form. Okay, so this is the leading term, this is the first sub-leading term, and then there are other terms which are known, but I have not written them down explicitly here. Okay. And this then we can compare with explicit classical and one loop contribution to this. Okay. This is the quantum gravity side of the calculation, and this is the result. Okay. And again you can see that there is exact agreement between the two sides. Here of course we don't know these dots because these require doing higher order correction in quantum gravity, okay, which are in principle computable because we have string theory, but in practice it's difficult. Okay. But you see that to the level that we can compute both sides, there is exact agreement between the two sides. Okay. So this again confirms that indeed AdS safety correspondence is not just a correspondence between classical gravity and conformal invariant quantum field theory, it actually captures the quantum aspects of gravity. Okay, so this is my summary. Okay. So what we have seen is that AdS safety correspondence gives us a new way of defining quantum theory of gravity in anti-inertial space-time. Okay. This in fact, in my view, is the main important impact of AdS safety correspondence. Okay. Although often we can use AdS spaces, but in general background. Okay. Because it should be clear from the discussion that holography allows us to define a theory of quantum gravity in AdS space, but not in more general backgrounds. Okay. But the idea is that once we learn enough from holography, perhaps we will have a way to define quantum gravity in a general background in a non-perturbative sense. Okay. So with that I will end. Thank you.
Time for a few questions.
No, it's much lower than the Planck scale. Yeah, so low energy basically means actually the zero energy limit, much smaller than a Planck scale. Right? So low energy means really low energy. Means really low energy.
Any other questions?
I had a question.
Yes.
This correspondence, it seems you don't have really an independent way to propose a correspondence without actually verifying on both sides. So it seems that you need to actually be able to compute on both sides before you can establish the correspondence. In which case, how will you use the correspondence to actually, apply the duality to do the non-perturbative?
Okay.
A little confusing.
Yeah. So first of all, as I said, there is some way of arriving at the correspondence, okay, without actually computing both sides, and that's that you look at the brane geometry, right? On the one side, you take the low energy limit or low frequency limit, and there are two different ways of looking at the low frequency limit. One is that you take out the dynamics of the branes and you take the low energy limit of that. Okay. And the other way is that you look at the gravitational solution and take the low energy limit from there. Okay. So let me go back to this example. But this is here, yeah. That we have two different descriptions of low energy dynamics of a system of M2 branes, right? One is as an ABGM model, the other one is as M theory on this. Okay, so this is the way we arrive at the conjecture equivalence. Okay, so in essence, there is an independent way of arriving at this conjecture. Okay, nevertheless, to be convinced of this conjecture, we have to test. Okay, we have to compare enough number of quantities on both sides to make sure that you have not made a mistake. Okay. But once you compute certain quantities, certain sufficient number of quantities on both sides, and once you are convinced that this correspondence is really true, then you can take this, okay, as a definition of quantum gravity and use it to compute other things. Right? So the idea that first the correspondence is well motivated because it comes from by comparing two defined low energy limit, two defined ways of taking low energy limit. Second, after that you can test it by computing certain quantities. Okay. But there are of course infinite number of quantities on both sides. Right? So once you are convinced of certain quantities, then you can take this as true and use it to define quantum theory. Right? You can ask the same. If you are really picky, you can say unless you have compared everything, okay, you cannot test it. You cannot accept that this correspondence is true. But that criticism will also apply, occur for the standard model, right? I can say unless you have tested every experiment, okay, for the standard model reproduces every experiment, okay, you cannot take this as the accepted theory.
More of non-abelian theory like you see where the low energy limit is hard to compute.
Yeah, I agree. So non-abelian theory like QCD is hard, okay, but a cousin of QCD, which is the inequality for super Young-Mills theory, right? There also the low energy limit is hard to compute, but some certain things can be computed, right? And then we can compare.
Any other questions?
Yeah. So the way you presented this, you gave a quite clear translation of certain quantities from the conformal field theory into the gravity language or the AdS language.
Yes.
In particular, correlation functions. And in the case of the CFT, one could probably argue that the correlation functions contain all the physical information of the theory. But if you want to go from the other way, it's not so clear. What observables of quantum gravity is one talking about, and what's the translation rule for those to go back to the CFT? I'm thinking especially in cosmological situations where observables at infinity are arguably not the relevant ones.
Yeah, so the point of this correspondence, okay, as stated, is specific to AdS spaces, right? And in AdS space, okay, because it has an asymptotic region, okay, there is a well-defined set of observables in quantum gravity, okay, which is that you look at the AdS partition function, okay, but the dependence of the partition function on the boundary conditions, right? Those are the observables which match onto the correlation functions in the conformal field theory. So you are right that in general gravity situation, right, you don't even know what the observables are, but because you are in AdS space, at least you have a clear set of observables that you can identify in the quantum theory of gravity.
Right, but even in the AdS space, is it clear that that's a complete set in some sense of observables? Or because AdS, all you're requiring is asymptotically AdS, but inside there could be an arbitrary mess. There could be black holes forming and evaporating and so on.
That is true.
There might be topology change, there might be baby universes, one doesn't know.
I agree.
To me, it's a bit of an extrapolation too.
Yeah, so if AdS CFT correspondence is true, right, which as I said, has not been proven, right, it has only been tested in certain examples, then it would say that anything that you can do inside, right, formation and evaporation of black holes, should be describable in terms of theory at the boundary. Right? Now this may or may not be true, right, but this is the underlying assumption in this AdS CFT correspondence.
Right.
That
would it be fair to say that we don't yet quite have the dictionary?
Yeah, we don't quite have the dictionary for
quantities to translate into the boundary.
Exactly. One very interesting question that comes here, for example, that AdS spaces can have black holes, right? And you can in principle ask what will be the experience of an infalling observer, right? In principle, that question should be answerable from the boundary theory, but nobody knows how to answer that question.
Any other questions?
Central result in standard quantum field theory is the issue of causality and locality.
Yes.
In fact, all the known generic theorems, CPT, spin statistics, depend on this. But here you are going to the Euclidean frame and also integrating over the matrix.
Yes.
So the issue is, and this space is, it's not at all clear that even time orientation is defined in this context. So the question is, how does causality fit in this framework and where is locality?
Okay, yeah. So first of all, in the conformal field theory, here of course you are integrated over metric, right? Conformal field theory is just a regular quantum field theory. So on the conformal field theory side, the way I have described the correspondence is by going to the Euclidean version, but there is also a Lorentzian version of the correspondence, right? So you can consider, for example, the time-dependent correlation functions in the conformal field theory, and that has its translation in the Lorentzian AdS. Okay. What the question that you are asking perhaps can be translated as to in the bulk locality, right? Given that the boundary theory is local, okay, because it is a regular quantum field theory, how do we see that the bulk theory is local, right? That the propagation in the bulk doesn't proceed faster than the speed of light. Okay. Now this has not been proven, right? That boundary causality will imply bulk causality. So far all examples that people have studied, it happens to be true. Nobody has been able to find a violation of causality and locality in the bulk, Okay? But this is certainly not proven.
The same thing, in the metric, well, you're dealing with Euclidean metric. That seems like Raphael would say.
But the boundary theory was a metric.
No.
Right? Boundary theory is a conformal filter in flat space time. That's what you're dealing with.
I'm talking about the bulk theory.
Yeah. So in the bulk theory, as I said, bulk locality is not at all obvious from the boundary viewpoint.
Yes.
Right? In the boundary, you know that we cannot send signal from one point on the boundary to another point faster than the speed of light. Okay? But how do you know, for example, that that implies that the same thing happens in the bulk?
See, in that context, what I want to ask is something that Raphael has been observed. Namely, the metric itself is a quantum operator, okay, in the bulk.
Yes.
And you have also made it, or this approach makes it Euclidean. Then it is not at all clear, at least to me, what is the meaning of time orientation.
No, see, the Euclidean one is just for simplification, right? You can describe AdS-CFT correspondence in Lorentzian space. Okay.
Yes.
But in Lorentzian space, I agree that the metric, of course, is a quantum operator. So when you make this correspondence, it's not that you have fixed the metric, right? What you have fixed is the boundary value of the metric. Okay, the boundary conditions are fixed because they are asymptotic infinity. But inside, the metric is a quantum operator. It fluctuates. Right? But all the observables, okay, at least the observables that are proved by AdS-CFT correspondence are boundary observables. So you fix the boundary, some boundary correlation function, and then if you want to do the calculation directly in the bulk, you have to quantize the metric, you have to think of this as a quantum operator, and you have to calculate the correlation function. Okay. So it's not that in the bulk we think of the metric as a static object, right? It's a genuinely quantum theory of gravity. Okay. And indeed, I mean, when these log corrections that I described, right? These, let me go back to this table. Oh. Yeah. So part of these log corrections do come from quantum theory of gravity, from graviton loops. Right? So indeed, in the bulk, gravity is quantum. Okay, it's only that we are fixing the boundary value, okay, because it's an asymptotic infinity, that you can fix and you sum of fluctuations. Okay. But let me emphasize again, what is not clear is that if we define quantum gravity in the bulk, okay, via the CFT and the boundary, okay, then how the locality arises in the bulk is not obvious.
So a different but related question. So some people have tried to extend AdS-CFT to things like DS-CFT and things which might be more directly able to cope with cosmological situations. Do you have any comments on that or opinions on where that?
I think it's at a very primitive stage. I mean, it's not even clear that it makes sense. Okay? Maybe it will make sense at some point, but right now, DS-CFT I think is only at the level of development, and one cannot take it very seriously, at least with the current understanding.
So I think we can take the remaining questions during the tea session outside. So let's thank him for a